Hey guys, it's Miss B, Tuesday Talk for February 4th, 2020. Few things we'll go over today: adding, subtracting, multiplying, and dividing polynomials. That's kind of to say, hey, what we've been doing. We're actually only going to focus on the dividing part since that's kind of been our focus this week. Completing the square to create vertex form, and imaginary or complex numbers. This would be the one that if you are gone for 1x, you would want to look into that because we're going to teach that while you're gone. All right, for a synthetic division or polynomial division, we have done a lot of the basic examples in class, but I wanted you to be aware of a few things that could actually happen. So look over here at our dividend. We've got x squared plus 2 minus 5x. I want you to know that it is important you write them in standard form, like in descending power order. So if I was going to do this one, I would have those coefficients in my synthetic process. I'd put my 3 out front, and here we go. So I'll drop down my 1, get 3, negative 2, get negative 6. And so since this dividend was a 2 power, I'll go down to a linear power of x minus 2 with a remainder of 4 over x minus 3. And that would be our final. So just a little, make sure you have that in the right order when you start making your coefficients out in order for synthetic. Here we have another situation where we're still dividing by a linear, but we are missing a term. So this could be written as x squared plus 0x plus 4. And we need to indicate that 0 when we're doing especially a placeholder for not only synthetic, but also for long division. Put my negative 1 in there for my 0, and now we just keep going through the process. So 1, negative 1, and positive 1. So I would have a linear term again, 1x minus 1 plus 5 over x plus 1. Again, not too much different in the process. I just want you to be cautious and aware of things that can change when you set the problem up. All right, now I have a cubic divided by a linear. There might be a time where I could show you, it's a little more pre-calc based, where you would take a cubic, say divided by an x squared, a quadratic equation. And then for those cases, you will have to use long division. But for now, I wanted to show you that you actually need the 0 of this. So in our box over here, we're not going to put negative 3. We need to know what makes this linear term 0. So if I didn't know which fraction that is off the top of my head, I could just go ahead and set up an equation equal to 0, and I will find out that the answer would be negative 3/4. So this is actually what I put in the box. And now for multiplying by fractions. Hooray! So I'm going to do in descending order. I've got a 12, a negative 11, a 9, and an 18. No coefficients were skipped, so I don't need a 0. And here we go. Bring down my 12. I've got 12 times 3/4, which would give me negative 9. Negative 9 and negative 11 give me negative 20 times negative 3/4 will give me positive 15. And 15 and 9. 24 times negative 3/4 makes negative 18. All right. Yes. Yay. And so hooray, no remainder on this one. We like that. So I went down a power. This will be 12x squared minus 20x plus 24. With no remainder, and it was a cubic, it reduces down to a quadratic. So just watch that 0, just something that will not be on the quiz. I won't do a linear term with a coefficient out here, but I just wanted you to see that. All right, next thing. We just learned this today on Tuesday. If you're completing the square, we talked about tiles, so I'm just going to build this for visual purposes. I've got my x squared. Now I need 9 x's, so the best way to split them up is evenly to make a square. There's 6 x's, and here's my 7, 8. To get this last one, I'm just going to make it kind of fuzzy. We'll call that a half, so we don't have to draw them smaller. So I know I have x squared and 9 x's. Their split is 4.5. So really the side length of this is x plus 4.5, and this is x plus 4.5. That's how we get that perfect square. What we really want to know then is what needs to go in here. Now first of all, I don't have any tiles to put in there, so that's going to be a problem. But let's figure out how many I would need. This is 4.5 by 4.5. We need to multiply that out and realize we want 20.25 tiles to fit in there. I don't even have any up there. So I'm going to not only need to get 7 to pay back my debt of owing someone else, if you will, I need 20.25 more than that. So I'm going to actually have to add on 27.25 tiles. But if I add it on, I'm going to use orange for my booger today, I have to subtract it off also, or I will have changed the equation by just adding on a random 27.25. All right, so these two terms together actually make the 20.25 I want for my perfect square. This is my booger who will just float down along for the rest of the time. So I'll have y equals x plus 9x, or sorry, x squared plus 9x. If I take 27.25 positive and subtract 7, I'm going to have my desired 20.25 with my booger of negative 27.25. And now, this doesn't really look fun to factor, I'm not going to lie, but let's just use our tiles over here. Let's just use this. It's a square. It was x plus 4.5 times x plus 4.5. You can actually use your tiles to make this term in the middle here. So I have my y equals, and I bring down my booger, and I am in vertex form. And so that tells me from the patterns we saw when we graphed them that my vertex is negative 4.5, comma, negative 27.25. And we found that out by graphing a whole bunch of vertex equations and realizing the pattern was the opposite of the value, the zero, if you will, and the value of the quadratic squared, and this value on its own. So keep in mind, vertex form, if you missed that, looks like y equals a times x minus b quantity squared plus c, where your vertex is actually b comma c. So we did learn that by just graphing a whole bunch of them, and vertex form is clearly there because it shows us the vertex super quickly. All right, and finally, I wanted to show you something about complex numbers. If we had a graph, I've got two functions graphed here. This one's my red one, this one's red, and this one's blue on the graph over here. Notice how the red one touches the x-axis 2 times, and the blue one touches it no times. A lot of times I would have you factor them, and look, if you factor the first red one, it has x plus 6, x plus 2. Those are actually the zeros, negative 2 and negative 6. That is why we factor. Going back to vertex form, we like vertex form because it shows us the vertex right off the bat. But if you have it in standard form, it shows us the y-intercept right off the bat, and you can see that that is happening over here at 12. On both of them, actually. If we factor them, it shows us the x-intercepts. That's why we like all three forms. Well, with complex numbers or imaginary numbers, when we try to factor this, nothing multiplies to 12 but adds to 6, so we try the quadratic formula. If you were to try the quadratic formula, and by magical powers here, I'm going to have this one up here. So here you can see with the quadratic formula, excuse me, this is your red one that I did. I've done the quadratic formula, and look what it gives you. X equals negative 2 and x equals negative 6. That quadratic formula gives us the x-intercepts that we can also get by factoring. But if it doesn't factor, we have to do the quadratic formula, and something crazy is going to happen with this one. Let's use our magical powers here as well. Poof, we have our quadratic formula here for the blue equation, and I got to this point down here and I see a negative 12, and this is our concern. When we have a negative, back when we did math 2 or even math 1 maybe with quadratic formula, when we get to this point we would simply write no solution. Let's think about what that meant again for a review. When you get no solution, that means this parabola does not cross the x-axis. It's not even touching it. Mathematicians do not like having no answer for an answer, so they made up numbers. And that brings us to imaginary numbers or complex numbers. It really is not that scary, but here's what we're going to look at it as. Your imaginary roots, which might not make any sense to you, are going to be x equals negative 6 plus or minus I times the square root of 12 all over 2. This I stands for imaginary number, and what it basically represents is the square root of negative 1. So I equals the square root of negative 1. I like to think of it in short ways as it just takes the negative out. It just can't handle it. Okay, put the I out front and let us know that it's represented there by a negative. It's definitely used in engineering, and you'll get to that more. I have not used it personally, well, except for my career is teaching you it. So anyhow, you will note that if you ever have a negative inside a radical, you will pull out an I, and this, guys, you can actually leave as your final answer. It's not super scary. Okay, I also want to show you a little bit of a thing too with reducing radicals. We talked about how this could be negative 6 plus or minus I times the square root of 12. Well, isn't 12 4 times 3? If I do that, I can actually square root this. I can write this part, this is called the discriminant, as the square root of 4 times the square root of 3, and I have my I out there. Well, we know the square root of 4 is 2, so I can put a 2 there. And then I leave my root 3 because it can't, there's no perfect square of that. So I could actually rewrite this as negative 6 plus or minus 2 I square roots of 3 all over 2. And if we haven't had enough fun, let me pull out the fact that look at all these terms. This second term, this first term, and the bottom term. Every single term has to have this, by the way, to have this happen. It can reduce because they're all divisible by 2. So my final answer would be x equals negative 3 plus minus I square roots of 3 all over 1, essentially. And I know it doesn't look pretty. It doesn't make your graph look any better. It still is floating. There are no zeros or roots, but they are imaginary roots. And we need to indicate that by something like this. All right, and so for one more quick example here, let's try the quadratic formula. I've actually already graphed this one, and you can too on Desmos. You'll see it does not cross the x-axis. So when we do, by our magical powers, here we have our quadratic formula all set up. I was careful to square the negative 5, put that in parentheses. Negative times negative makes positive. I have a square root of a negative 15. Again, normally we would stop, say there's no solution, but our final answer will be this. 5 plus or minus the square root, oh, I forgot my I, oops. I times the square root of 15 all over 2. And guys, this one is done. We can't reduce it at all, and here's why. 15 only is a 5 times a 3. Neither of these are perfect squares, so nothing comes out. So we just put the I out front to represent this negative. The 15 stays, and we can't reduce since there's no term out here, and 2 doesn't even go into 5. So there you have it. That is kind of the gist of complex numbers. They definitely are the same as quadratic formula, just you have that negative, you pull that I out front, and try to reduce that radical if you can. And lucky for you, we are almost out of time here. They limit me to 15 minutes. You're welcome. But this is your summary for the imaginary numbers or complex. I is equal to the square root of negative 1. And so actually mathematicians had so much fun creating imaginary numbers, they said, oh, we can add them. So if someone says, what's 5i plus 7 minus 2i minus 3? You can still do operations. Well, 5 imaginary numbers take away 2 imaginary numbers is 3 imaginary numbers. And 7 take away negative 3 would make 10. You can also multiply them like 2i times I minus 4. But here's where it gets a little crazy. 2i times I is 2i squared. 2i times negative 4 makes negative 8i. When it comes to I squared, think about it. If I is the square root of negative 1, I times I would be square root of negative 1 times the square root of negative 1. Well, when we do that, what happens when you take a square root of negative 1 and you square it? Well, square rooting and squaring will cancel each other out, so you're just left with negative 1. Kind of like 2 wrongs might make a right. Basically, 2 imaginary numbers multiplied makes a real number. So this I times I, which is I squared, here's how I broke it down. It's really negative 1. It's crazy. So this I squared, we're going to replace with a negative 1. So I have 2 times negative 1 minus 8i. My final answer is negative 2 minus 8i. We'll get more of these practice. You can always ask more. But guys, essentially you can add and subtract imaginary and real numbers together, and you can multiply. Your last little hint I'll give you for today is I squared is always equal to negative 1. And that's because of this math we did up here in red. So don't forget, if you ever do multiply and you get I squared, you need to treat it as a negative 1 and substitute that in there. Hope you've enjoyed this rendition of Tuesday Talk, what's it called, that thing, and kind of long today, but lots that we're going over, and especially for you kiddos who are gone. Hopefully you can learn something. Khan Academy, come see me. Have a good day. Burke, out.